estimate the thermal conductivity. As we have done in transfer coefficient also. I'm not going to discuss each and everything minutely. Only the thing is, you should remember that there are ways. There are some ways to estimate viscosity, thermal conductivity, and diffusivity. Theoretically also, and empirical equations are also available. If not, you cannot get for your case. So you need to design appropriate this thing experimental setup to get these values. Okay. So this thermal conductivity empirical graph we have discussed, and exactly same thing we have done for viscosity also, and we have solved this problem. So where this critical pressure, temperature can be used. So critical temperature, critical pressure, these are the values, and using this you can get critical viscosity, critical thermal conductivity, and there are some of the books where critical thermal conductivity is also given. Okay, critical thermal conductivity is also given, so you can use that critical thermal conductivity and get the value of thermal conductivity at given temperature and pressure using this empirical graph. This is already we have seen for viscosity also, for thermal conductivity also, and then this is the similar kind of Maxwell equation, similar to Maxwell equation. This is, I think, Chapman equation, early Chapman equation. So where this equation is derived for a low density. This holds good for low density monoatomic gas. It is not derived for. It holds good. So fitting is very good. Okay, it will give very accurate value for low density monoatomic gas because of assumption. Why this limitation? Because of assumption. So it doesn't mean that you cannot use this equation for polyatomic gas. You can use this polyatomic gas, but certainly it is violating assumption to higher extent, greater extent. So certainly whatever values of thermal conductivity you will be getting, so that will have some error. So there are some relation. This Boltzmann constant can be related with a gas constant and Avogadro's number. So this is Boltzmann constant. So you can, and this CV is related to this actually. CV is related. So CV can be rearranged here. CV is a molar heat capacity at constant volume. So this relation between CVR and Avogadro's number. So you can go in discussion in thermodynamics. So you can, and different value of CV actually, different unit of CV in CGS unit. So you will have capital M will be involved. In SI unit, capital M is not involved actually. This is molar heat capacity at constant volume. Okay, molar, and sometime heat capacity, that will be mass. So so it all depends upon nomenclature wherever it is given. So you should go, and that is what I am telling, that whenever you are discussing any parameter, units are very important. Okay, units are very important. So, and this is thermal conductivity. Thermal conductivity will be given. So this is the Chapman equation. So advanced Chapman equation. So, and this equation is obtained for, say, obtained from first of all kinetic theory, input from kinetic theory of gases, and then statistical thermodynamic input, and then they got this collision diameter and collision integral. When they have simulated these molecules on molecular level, and you can get this value, collision diameter and collision integral value. So this is the approximate equation. So which is, this Chapman equation is similar to Maxwell equation in momentum transfer. Momentum transfer, this is identically similar. In fact, they can be related also, because this value of this collision diameter and collision integral are same in both momentum transfer and heat transfer. This is heat transfer, and for momentum transfer and heat transfer, both values are same actually. This collision diameter and collision integral. So certainly we can have relation between thermal conductivity and viscosity based on this Chapman equation and Maxwell equation. This is what we have done yesterday. So this is the Maxwell equation, where we'll have this collision diameter and collision integral omega mu, and this collision diameter and collision integral this thing actually, and these both are same actually. So dividing this equation 1 by 2, dividing equation mu by k, so and rearranging the equation, so you will get k equals to 5 by 2 cv, okay, cv into mu, and then cv can be correlated with a gas constant. So these are the thermodynamic relations. cv equals to 3 by 2 r by m. This is what I was telling. So sometime you will not get this m. M is a molecular mass. So that depends upon in which unit you want specifically. Okay. It is specific to this actually molar or mass. Okay. So this 3 by 2 r, substituting this 3, combining this 3 and 4. So you will get equation 5, which will be relating thermal conductivity with viscosity using ideal gas constant and molecular mass. Okay, 15 by 4 R by M. And similar thermodynamic relation is available for Cp also. Okay, Cv can be related to Cp using ideal gas constant. Okay, this is Cp equals to 5 by 2 R by M. So here you can have this 5 by 2, rearrange here, rearranging 5 and 6. Okay, combining this 5 and 6 and rearranging the equation. So you will be getting Cp equals to K equals to Cp plus 5 by 4 R by M. This is ideal gas constant M and mu for polyatomic gases. This is true for polyatomic gases. So everything can be used for polyatomic gases because some thermodynamic information is used specific heat at constant pressure. So this will give you more accurate answer for polyatomic gases. Okay, so because some more additional information is involved. So this is what we have discussed yesterday. So we'll try to solve some of the problem based on this formula, then based on maybe this formula, all the formula we'll try to solve the problem, and we'll end this discussion of thermal conductivity, and briefly I will explain what is given for diffusivity. On same line you can discuss for diffusivity also, how to estimate the diffusivity. Just it will be just under so as far as transport phenomena goes, so we are not going to go in details of derivation of this equation, but you should remember this name of the equation, and there are equations available. These are very very important. So at least you should know that diffusivity also, but you can try on your own actually solving this problem. So just we'll conclude this part in today's class. From tomorrow we will be starting the velocity profile, derivation of velocity profile. There will go in details actually. Here this derivation of this equation will not cover. So and again same thing. Okay, it's empirical formula for thermal conductivity of mixture of gases. So identical equations are there. Okay, identical equations we have seen in momentum transfer also. This will be interacting parameter alpha beta. So if I assume that the interaction among all the compounds are similar, then simply you can use this formula. Interaction is similar means this will be equals to 1. This will be equals to 1, and then this x beta varies from 1 to n. Okay, it will be equals to 1. So this will be summation of alpha into k alpha. So simply you can, but when you consider the interaction so difference in interaction between the molecules, so you can use this formula to get the thermal conductivity of gaseous mixture. This is clear to everybody? Anybody has any doubt? Okay, compute the thermal conductivity of neon at 1 atmosphere and 273.2 Kelvin. Okay, so I want just a procedure how to handle this problem, how this problem can be solved based on whatever input you have. Based on whatever input you have, so you just give me Ayush. Ayush Pimpalwadkar.
Yes, sir.
So why you are not logging with your roll number?
Hello, sir. Am I audible?
Yeah, yeah. Why you are not logging with your roll number?
Oh, sir, I have been doing, sir. I don't know what happened today exactly. Extremely sorry.
So you are expert in this social media, everything, and this thing. You should know what is happening.
S- Sir, I really have no idea because last time also when you checked, my name has been my roll number and then my name.
PT 19 CME 026 Vijit Babu. 26 Vijit Babu. Vijit Babu 26. Roll number 1 Abhinav.
Yes, sir.
So just get me a brief overview. Now already we have discussed something. So I know that you can solve this problem easily. But how many ways are there to solve the problem?
Uh, Sir, first way is that from the graph we can solve
Very good, excellent. That is first way. Second way is
empirical equations.
empirical equation. Which equation that empirical? What is the name of that equation?
Chapman equation.
Chapman equation. Okay. And third way,
Uh, Third, yes, sir, that relation which we have derived in the
yeah. What is that? Third, what is that?
Eucan equation, I guess.
Yeah, Ekman equation. What?
Mm.
How to go for that? How to use this equation? Very good. So how to use this Eucan equation?
Uh, so we can find uh, CP and CV, I guess.
Okay, CP and CV you can get it from data book.
And then some mu also from
Mu cannot you can you get from data book?
no, sir.
Yeah. So how to get the mu?
So I guess from the graph.
Yeah, very
Empirical.
good. So we have discussed the empirical graph for estimating viscosity also. So you can get a critical temperature, critical pressure, and critical viscosity. Temperature pressures are given, so you can get the value of viscosity from empirical graph. That is third way. And fourth way is, what is the fourth way to solve the problem?
Uh, Sir, the last equation which you have shown that about polyatomic gas.
Yeah, that is what I am telling. Na? So this you can get it from data book. All this value is available in data book. CP,
Mix.
gas constant, molecular mass, and this you can get it from empirical graph for viscosity, which we have discussed in couple of class back. And what is fourth way? Anybody can give input related to regarding fourth way to solve this problem? Yeah, roll number 6, Aksh.
Yes, sir.
Yeah, fourth
Sir,
way to yeah, tell me.
sir, we can do one thing. We can find out mu using that equation only, a Chapman
Maxwell,
Engskov equation.
Maxwell equation. Very good. Very
Yes, sir.
good. Yeah,
And,
excellent. So,
and then we can, yes, sir. Then we
yeah,
can use it in the Yukne's question.
very good,
So
very
that
good,
would be a
excellent. So there are four ways to get the viscosity here itself, whatever data we have. First of all, we can use an empirical graph for thermal conductivity. Get the value of critical temperature, critical pressure, and critical thermal conductivity from data book. And at given temperature and pressure, get the value of thermal conductivity using a empirical graph. Which empirical graph I am talking about? This empirical graph. Okay, this is first way. First way is get the value of critical temperature, critical pressure, critical thermal conductivity from data book. So at given temperature and pressure, get the value of thermal conductivity. This is first way. Second way is you can use this Chapman equation. Okay, using Chapman equation, get the value of collision diameter, collision integral from data book. Substitute in this equation at given temperature you can get the thermal conductivity. This is second way to get the thermal conductivity. Third way is use this Yuckman equation. Okay, use this Yuckman equation so you can get this Cp value from data book, R and this M, okay, from data book, and viscosity can be estimated again by two ways. First one is a use empirical graph for viscosity. Get the value of critical temperature, critical pressure, and critical viscosity from data book. Get the value of viscosity at given temperature and pressure, and using this Eucane equation, you can get the thermal conductivity value. Okay, and fourth way is get the value of this viscosity using Maxwell equation. Using Maxwell equation and substitute in this equation, so you will get a thermal conductivity. So you can use any way. Certainly, based on assumptions added, there will be plus minus error according to that. For that, you need to have a detailed understanding of statistical thermodynamics and this about this constant and all. So better you go through all this constant. Okay, theory of all this constant. What is ideal gas constant? What do you mean by specific heat at constant pressure, specific heat capacity at constant pressure, heat capacity at constant volume, how they are related to this R, how they are related to Avogadro's number, how they are related to Boltzmann constant. All these you can go in. So accordingly, you can decide which is more correct and which way will give you more correct answer of thermal conductivity. Okay, so here what you want to use is you can use this value actually. So you can use Chapman equation. Okay, this is the Chapman equation. So so you using this data book, so you can get the value of collision diameter and collision integral and substitute here and get the value of thermal conductivity. So you can see actually collision diameter and collision integral. So what is the temperature and pressure? So temperature is 273.2 Kelvin and pressure is 1 atmosphere. So what is the value of collision diameter and collision integral? Roll number 25, Nivas. Roll number 25. Roll number 44, Narendra.
Yes, sir.
So what is the value of collision diameter for a given problem?
It is 2.789, sir.
Very good. And how to get a collision integral values?
Collision. So given using T by K, sir, we can find
Yeah. What will be value of collision integral?
uh, 0.821, sir.
Huh?
0.821.
821. How you got that 0.821?
Sir, using T epsilon by K, sir.
What is the value of E epsilon by K?
10.4, sir.
T epsilon by K or KT by epsilon?
KT by epsilon, sir.
KT by epsilon. How you got KT by epsilon? How you got KT by epsilon?
Inverting E by K, sir.
Yeah, yeah. This
Inverting.
epsilon by
Yes,
this divided by temperature.
yes, sir.
Okay. So 35 divided by this temperature will give you epsilon by KT,
Yes, sir.
and temperature divided by this will give you temperature divided by this will give you KT by epsilon. So 273.2 divided by 35.7. How much that is? So
Two.
this is the value of epsilon. Okay, collision and delta. Okay, collision diameter. So collision integral. So first you divide this by this.
It will be
273 divided by 35. How much it is?
10.45, sir. It is.
10.45. So it is in between these actually. And
Yes, sir.
10.4 is very close to 10. So you can take the value something around zero point 0.8, just less than 0.824. So something around 0.822 or 820, something like that. You can interpolate this value here and get this value. Okay. Now you have collision integral and collision diameter. This is collision diameter and this is collision integral. Collision integral is between this, and use Maxwell equation. So use Maxwell equation and substitute this. So here 8 to 1 you can say 8 to 1. So you will get a thermal conductivity value. So what is the value of thermal conductivity, Narendra?
I'll calculate, sir.
Now as I told, you go home, okay, and calculate the value of thermal conductivity by remaining three ways and compare this value and write your conclusion, okay, which is more correct and why. For that you need to read a input from thermodynamics also related to Cp, Cv, then Boltzmann constant, then Avogadro's number, then how they are interrelated to each other, where they can apply more accurately. Okay, so you estimate the thermal conductivity using all different four methods. You can say methods, and compare this value of thermal conductivity. Okay, so this point 1.338 into 10 raised to minus 4 calorie per centimeter second Kelvin. Okay, and this measured value is given. This is experimentally measured value. This you can say, you can take it as a correct value. Okay, you can take it as a correct value, and you now calculate the error between this correct value and calculated value. Likewise, you calculate the error between all four estimated thermal conductivity, and you discuss where you are getting maximum error and why you are getting maximum error. Okay, so we will move on to next problem. Estimate the thermal conductivity of oxygen at 300 Kelvin at low pressure. At low pressure means you can consider close to 1 atmosphere. Okay. at low pressure. So pressure, even though it is not given, as it is telling that low pressure means close to 1 atmosphere. So how to solve this problem? Again, there are 4 ways to solve the problem. First one is the empirical graph directly you can use. Get the value of critical temperature, critical pressure and critical thermal conductivity of oxygen from data book. So at 1 atmosphere and 300 Kelvin, get the value of thermal conductivity from empirical graph. That is one way. Another way is you can use a Maxwell equation. Okay, Maxwell equation, get the value of collision diameter and collision integral, and using not Maxwell equation, using Chapman equation, so you can get the value of thermal conductivity. Third way is you can use so here actually this is mono, you can consider this as monoatomic or polyatomic also, polyatomic cell. So Eucane equation you can use. There you can get the viscosity from empirical graph for oxygen at 300 Kelvin and 1 atmosphere. That is one way. And fourth way is again get the viscosity from Maxwell equation, use Eucane equation to get the value of thermal conductivity. These are the 4 ways. So we'll see what is happened. So this you can use Maxwell equation. So how to go for Maxwell equation? Roll number 59, Nikita.
Yes, sir.
So what is needed data here?
So for the Maxwell equation or for the Chapman equation?
This Chapman equation, not sorry, so Chapman equation.
Yes, sir. So we will use the appendices to find the value of sigma and the collision integral.
Yeah, and
We will substitute.
yeah, maybe just a point to be noted here. Sometime here it is defined with a collision diameter, a collision integral. So this might be given in some other format in different books also. So accordingly, that data will be available in their appendices actually. So this collision diameter divided by molecular mass, something will be there. That depends upon book to book, because here we are following that BSL book, and this nomenclature and dimensions are according to that actually. So from that appendices, I will get this collision diameter and collision integral. This is what she was telling. Appendices table E.1, Lennard-Jones potential parameters and critical property. So which properties are important, Nikita?
Sir, first we'll find the molecular weight. It's given 31.999.
Okay, 31.999. Then
Yes, sir. And then collision diameter is 3.433.
3.433, very good.
And then we need to find the KT by epsilon. So we can see the epsilon by K is 113. And we know the temperature is 300 Kelvin.
So what is
So then we'll find KT by epsilon.
epsilon by K? How much? Epsilon by KT, first of all. Epsilon by KT you calculate, or KT by epsilon. So this divided by this.
Hello, sir.
How much is KT by epsilon? KT by epsilon, value of KT by
Hello, sir.
Yeah,
Sorry, sir, my mic just dropped.
what is the value of KT by epsilon?
So it will come around 2.65. So
2.65. So something, this you can interpolate, and some
yes, sir.
value between this actually, between 1.08 and 1.06, something close to say, no,
1.07 sort
no,
of we can
this
take.
is 6.9. This is close to 7 actually. It will be something around 1.075. Okay.
Yes, sir.
1.075. So this use this value 3.443 and one close to, you interpolate these values. and substitute. So these are the values. So let us see what are given. So you can see 1.074 and 3.774. So what is the value here?
Yes, sir. Just a second, I'll calculate.
So this is 4.81 into 10 raised to minus 5 calorie centimeter per second Kelvin, and that is equals to 0.0201 watt per meter Kelvin. Okay, thermal conductivity, just unit conversion. Okay, 0.0, and experimental values are 0.02657. So you can see there is a huge error. There is almost a 20 to 25% error between experimental value and calculated value. Experimental value is giving lower conductivity value as compared to experimental value. So, and this will happen as it was explained when we were using engineering correlation for estimation of this thing also, actually, estimation of heat transfer coefficient and mass transfer coefficient. Similarly, I can use a Maxwell equation. Okay. How to use Maxwell equation for this estimation of thermal conductivity? Roll number 85, Karthik.
Yes, sir. For Maxwell's equation, we will require Boltzmann constant.
Maxwell equation will require Boltzmann constant.
Yes, sir.
This is
So,
Maxwell equation actually. This is Maxwell equation.
oh, okay, sir.
So anyway, you will get same constant if you use Boltzmann's constant and this all other constant values you can get, and you can rearrange this equation. What are the data required in this Maxwell equation?
Sir, we will require sigma collision diameter and collision integral.
Okay, and then you can use either this equation or this equation, equation or this equation to get the value of thermal conductivity. So, which values you will be using here?
Sir, for oxygen, we have sigma as 3.433, then epsilon by k as 113. Then
Oh,
we'll do epsilon kT by epsilon, that is temperature upon epsilon by k.
okay. So, what is
Yeah.
the value of epsilon by kT by epsilon?
Epsilon by kT will be 300 upon 113, that is 2.65.
And so, what will be
So
the value of collision integral for viscosity?
2.65, it would be intermediate value, so it should be less than 1.08, so it would be approximately 1.07.
75. Already we have
One,
estimated. All these
yes,
values
sir.
are because you can see collision integral are same, collision diameter is same. So already
Yes,
these
sir.
values are this you can get it from data book. CP is 7.019 calorie per gram mole Kelvin, and accordingly you can use the value of gas constant. Accordingly you can use the value of gas constant. This is the value of gas constant you can use. Okay, this is the value of gas constant you can use, and you can use equipment equation actually. So, and this is viscosity. So same values already we have estimated. So using this, viscosity is 2.065 into 10 raised to minus 4 gram per centimeter second. So Eucman approximation of thermal conductivity Cp plus 5. This is just a rearrangement. Okay, this
Yes, sir.
molecular mass is taken out. So this will be a per unit molecular mass. Okay, this will be molecular. This was per unit molecular mass. Now this will be a per unit mass. So that is what this unit conversion is there. So, and this is the value actually. So rearranging everything, okay. So I got thermal conductivity K equals to 6.14 into 10 raised to minus 5 calorie per centimeter, and this is K equals to 0.0257 watt per meter Kelvin. So this is, and this is very close to experimental value. Okay, this is very close to experimental value. So now you should not taken it granted that all the time this Maxwell equation and combination of Maxwell equation and Euclidean equation will give you more correct value than using only Chapman equation. Okay, so it is not the case. It depends upon situation to situation, temperature, pressure condition, and which compound you are looking at. So where the approximation taken for derivation of this equation fitted well, that equation will give you a more correct value. It doesn't mean that okay all the time this using Maxwell equation and Euclidean equation will give you more correct value. In this situation, for this oxygen at 300 Kelvin and low pressure, so it is observed that Maxwell equation and Euclidean approximation gave us a very correct value as compared to experimental value. Now you can use both the empirical graph and compare the viscosity value where you are getting maximum error, and just conclude your observation, your conclusion, why you are getting maximum error in which case actually, and minimum error in which case. Okay, so and this is already we have solved one problem actually. Exactly similar problem is solved for viscosity, getting the value of viscosity for this thing actually. That time we have used this data. Now replace the data by thermal conductivity. And get the uh, value of thermal conductivity of the mixture which is containing 13.3% carbon dioxide, 3.9% this thing oxygen, and 82.8% nitrogen. Okay, 82.8% nitrogen. So you can use this data. So and get the value of this integral first. Okay, get the value. So try to solve it at home. So this integral values you will get 0.76, 1.057, and substituting this you will get 154 into 10 raised to minus 7. Okay, 584, not 154, 584 into 10 raised to minus 7 calorie per centimeter second Kelvin. So certainly, okay. So this contains maximum amount of nitrogen. So you can see our this thing is also very close to nitrogen thermal conductivity. This is just a, you can approximate, you can cross check your answer is very correct or wrong. Okay, if you are getting thermal conductivity say less than 382 is not at all possible. Less than 382 is not at all possible. Greater than 627 is not at all possible. But as nitrogen content of nitrogen is 82%, certainly it will be closer to this. Okay, just rough estimate you can get for thermal conductivity of mixture. This already we have solved, so you can go home and solve this problem. Now thermal conductivity of solid. So for metals and non-metals, so crystalline materials, so for metal temperature, with temperature thermal conductivity decreases. For non-metal thermal conductivity increases with this thing actually. And there is a nature of material also will play a important role in deciding the thermal conductivity of solids actually, like crystalline. So non-metals can be categorized into amorphous, dry, porous solids, and all. So all this will have some specific nature. So there is Lorentz equation. This is called as a Lorentz equation. So using which, so this is Lorentz constant. If you have electrical thermal conductivity, Ke is a electrical thermal conductivity, and this value of K by Ke at temperature is given. Okay, at various temperature is given. and this value is between 22 into 10 raised to minus 9 to 29 into 10 raised to minus 9 whole square plus Kelvin. Now, given a temperature and electrical conductivity, so I can get the thermal conductivity of material, okay, at a given temperature. This is Lorentz equation. This is the one of the way using which you can get the value of thermal conductivity for solids. Okay, this is one way, and other way, so is not given in a book. It doesn't mean that there are no other ways. Okay, just we are covering whatever covered in a book actually. This is again Maxwell equation when thermal conductivity of composite solids are there. So you have mixture of solids, composite solids. So and concentration volume fraction is given. Okay, small volume fraction. This Maxwell equation can be used. Large volume fraction. This Rayleigh equation can be used, and this equation you can use to get the thermal conductivity of composite solid. Where so you can say effective thermal conductivity corresponding to a thermal conductivity of base material. Okay, thermal conductivity of base material, which is taken as a K0, and K1 is a which is material added to that. Okay, in volume fraction part K1. So this will give me a thermal conductivity, effective thermal conductivity. So this is all about thermal conductivity actually. So now what we have covered till now, that we'll discuss briefly actually. So you can go in this book actually. Can you see this book PDF? Is visible to you? Book PDF?
Yes, sir.
Okay, so this is the book of this BSL. Already once I have shown actually. So once I have shown. So this is BSL transport phenomena. Okay, transport phenomena second edition by Bird, Stewart's and Lightfoot. So you can see this part 1 is momentum transfer, part 2 is heat transfer, and part 3 is mass transfer. This book is divided into 3 parts. Go to part 1. This chapter 1 we have covered, and just to, what we have covered some of the part here, and this we have covered actually recently in past couple of this pressure and temperature dependence of viscosity. This is the empirical graph, and then we have solved this problem, and this is you can see kinetic theory of gases, molecular theory of viscosity of gases. So you can use this kinetic theory how to derive these equations and all. So molecular interaction, low molecular interaction, and then they have discussed how that Maxwell has given this equation actually using Lennardson potentials and all. Okay, this is collision diameter, collision integral, and this is how to get the viscosity of the mixture. So this is what we have solved the problem. Then viscosity of the solid we have discussed actually. So this is viscosity of the solid. Again, from molecular theory we can get this equation, and then viscosity of emulsions. Okay, so briefly this we have discussed actually. This is all we have discussed from this chapter number 1. Okay, and then if you go to heat transfer, then chapter number 9, this is what we were discussing. Theory of thermal conductivity of gases at low density. Again, you can say similar mean molecular speed and collision and everything, this kinetic theory of gases and their interaction. So that gives this Chapman equation. This is Chapman equation. So which we have used here. This is collision diameter and collision integral. Okay, collision diameter and collision integral. These are the thermodynamic relation which is used actually, and this is Eucken equation. Eucken equation. So, and this is the thermal conductivity of mixture. Okay, and then we have used that empirical graph, and these all this thermal conductivity of solid. They have solved problem, unsolved problem for everything actually. So you can practice all this to get the thermal conductivity of solid gases. Okay, this is what we have covered. Now you come down here in mass transfer. So in chapter number 17, so in chapter number 17, pressure and temperature dependence of viscosity. This I am leaving it to you. Okay, you need to study this part. Actually, this will be repetitive again. You can see similar equation is given. Similar empirical equations are given, which is relating diffusivity with pressure and temperature. Okay, this is similar experiments. Empirical equations are given. Okay, then this is similar empirical graph is there. Here you can see this is the reduced temperature, this is reduced diffusivity, and this is the reduced pressure. Okay, so this empirical graph is similar. Okay, and then you can see you can have a critical diffusivity. This is called daa. daa is called as a self diffusivity, diffusivity of hydrogen and in hydrogens. daa, self diffusivity. This is the empirical equation which will give me a value of critical diffusivity. Critical diffusivity. So here some difference will be there actually. Here instead of only diffusivity, it is concentration multiplied by diffusivity. Critical, at critical temperature and pressure, this is self diffusivity. This is a diffusivity of compound A in B. Diffusivity of compound A and B at critical temperature and pressure. So using individual critical temperature, individual critical pressure, so you can get the value of critical diffusivity of one compound in another compound. So again, you can use this equation to get the value of diffusivity. So these are the equations. So this you need to work on your own. Actually, how to use this empirical graph, getting the critical diffusivity and get the value of diffusivity. Solve problem are there. So you go home. This is the homework for you. So, and theory of diffusion of gases. Again, you can see. So same kinetic theory of gases, and then relation and discussion, interaction, molecular forces and all. So they have derived this equation. This equation is very, very important. Okay, this equation is very, very important for chemical engineer. So we might have used this equation almost 100 times till now. This is called as a Chapman equation. This is called as a Chapman equation. So where we have used this equation, so diffusivity is directly proportional to temperature raised to 3 by 2. You can see here. So this equation, so this is Chapman equation. So this here you can see diffusivity. Okay, diffusivity is directly proportional to temperature raised to 3 by 2 under root of T raised to 3. Okay, diffusivity is directly proportional to temperature raised to 3 by 2 and inversely proportional to pressure. This is pressure actually. This is pressure. So this equation so many times we have used. This is called as the Chapman equation. So this is equivalence of Chapman equation in heat transfer and Maxwell equation in momentum transfer. So this equation you can use to estimate. Again, you need a collision integral AB. This collision diameter AB. So how to get this collision integral AB? Okay, that formula is given. That can be related with a collision integral of A and collision integral of B, and this epsilon AB, how to get under root of epsilon A, epsilon B. So using that you can estimate the diffusivity actually, and this self diffusivity also you can get the using same Chapman equation. So these are the equations and solved problem. Then theory of binary liquids. Okay, some of the equations are available. This is the assignment to you, homework for you to go through everything. Okay, just read the equation and solve the problem and know how to use that equation, so that you will get a feel that there are equations available which will give me a value of diffusivity for different compounds and everything, and how to use these appendices and given data. Okay, so which appendices this you can say theory of diffusion of polymers are there. Okay, some discussions is there, and this solved problem and unsolved problem is there. So where to get these appendices is, you can see here appendices A is there, so which we will be using in future, B we will be using in future, C we will be using in future, D we will be using in future, and this is what we have used appendices uh, E. Okay, appendices E. So intermolecular force parameter and critical property and functional prediction transport property of gases at lower density. So here, so you can see this is collision diameter is given, this epsilon by K is given, critical temperature, critical pressure, critical volume, okay, per unit moles, volume per unit, critical viscosity is given, critical thermal conductivities are given, critical thermal conductivities are given. So these data you can use, and then these are the value of collision integral and for viscosity and thermal conductivity, and this is the collision integral for diffusivity. Actually, these values you can see. So some brief information is also given. Actually, this you can use. Okay. So till now, what we have covered actually. So and hereafter we will be shifting our gear actually. We will be moving on to estimation of velocity profile, estimation of temperature profile, and estimation of concentration profile. Hereafter, all classes are devoted for that only. That we will discuss in detail. So what we have covered till now is this chapter number 1, some part of chapter number 1, then some part of chapter number 9, okay, some part of chapter number 9 from this book, and some part of chapter number 17 in this book. Okay, that is what we have covered. And then what we have covered is interface mass transfer. So this some part of chapter number 6 we have covered. Hey, anybody has any doubt?
అది ఏదో సేఫ్టీ మెజర్ అనుకుంటా గర్ల్స్ కన్నా ఎవరికైనా.
So what we have covered is some part of chapter number 6, interface transport is covered, and then some part in here, heat transfer also we have covered from chapter number interface transport. Okay, temperature distribution, this chapter number 14, interface transport in heat transfer, and some part of, you can see, in mass transfer we have covered actually some part in interface transfer in. So from this BSL book, what chapter we have covered actually? So we have covered chapter number 1, and then where I have written somewhere. Some part from chapter number 9, some part from chapter number 14, 17, and 22. These are the 6 chapters. You read it properly, whatever covered part, and make a notes accordingly. Okay, and then this we have used similar data from this book also. So where we have covered chapter number 2 as it is. Okay, this chapter number 2 we have covered as it is actually. This as it is we have covered chapter number 2, and then chapter number 3 we have covered as it is, dimensional, this molecular flux and dimensionless number. Then here interface flux and dimensionless number. So this chapter number 3, and this dimensionless number for interface flux we have, and then these analogies are given here. And then chapter number 4 also we have covered engineering correlation. So we have covered only 4.2 in a class, and remaining is for your assignment. Okay, take home assignment. So you need to solve on your own solved and unsolved problem of chapter number 4. This is what we have covered till now. So what we are going to cover hereafter is, so now here you can see, so we have covered discussion about fluxes, then estimation of friction factor, heat transfer coefficient, and mass transfer coefficient. So we have covered viscosity, thermal conductivity, and diffusivity. Now remaining is only this. Okay, this part we are going to start in tomorrow's class actually. How to get the velocity profile for how to get the temperature profile, and how to get the concentration profile. So anybody has any confusion over here? Actually, what is assignment, take home assignment? You need to work on your own also. So don't rely on just topics covered in a class. So you should cover all the aspects at least for laminar flow, simpler problem, simpler situations and all. So how to get this value for simpler equations, simpler situations. So where specifically partial differential equations are not involved. So steady state, laminar flow, then kind of thing actually that you should be able to do. So this is what covered in this basic transport phenomena. Is it okay? Anybody has any confusion, any questions related to this? From tomorrow we are going to switch over to some other topic actually straight away. If there is no question, so you can leave the class. Thank you very much for attending this class. We'll meet in tomorrow's class.
Sir, I had a question.
Yeah, roll number 59.
59.
Nikita.
Yes, sir.
Yeah, tell me.
Sir, so actually, when we are plotting the empirical graph, what exactly is the significance of plotting the reduced properties as opposed to, just plotting directly the k values or the t values?
That is what I am telling. This is, you can say, empirical graph, but they are converted into dimensionless number actually. These are dimensionless. So importance is same empirical graph can be used for large scale also, large scale operations. Same empirical graph can be used for small scale also.
Okay, sir.
Okay. That
Yes.
so as such, so I will say that okay, it will not make any differences. This is how you will see. Okay. So you want to put some chemical engineering into you. So you add some information from chemical engineering and put the information. So it will be widely used. That information will be widely used. So that is only the thing. Otherwise, you can have temperature, pressure, and this thing also viscosity. Maybe that look very vaguely, and they have tried different ways, and they have concluded this: if you use reduced temperature, reduced pressure, and reduced pressure and reduced viscosity, then the graph is looking systematic and it is following some theoretical trend also, partial theoretical trend and fitting the experimental value properly. Hence, they are put in that form.
Okay, sir. Got it. Thank you.
Yeah, anybody else?
Sir, for the assignment part, chapter 4 from Ismail Tyson book, right? And 17 from BSL book.
Ravi, I am not able to hear you properly. Can you talk slowly?
Sir, for the assignment part, we need to cover chapter number 4, whole chapter number 4 from Ismail Tyson book.
Yeah. No, that is what I am telling, that information given is similar to that chapter number 6, 14 and 22. Same information is repeated in different language.
Yes, sir.
Okay. Same information is given in chapter number 6, 14 and 22 in BSL, but that is in different language. Only the viewpoint is different. This is how BSL has explained. This is how Ismail Tashan has explained.
Yes, sir.
Okay.
Sir?
Yeah, Karthik.
Yes, sir. Before Chapman-Enskog equation, we had seen an equation which involved Boltzmann constant.
Yeah.
And in that, for Boltzmann constant, we had seen R by Avogadro number. Now,
Yeah.
again, we had seen ml square by small t square by ml square by small t square into temperature. So that small t, sir, what is it? And for molar heat also we had involved that small t.
Yeah, here you are telling.
Yes, sir.
Yeah, this
With
is actually dimension time. This is
dimension time.
generally this diameter, this is molecular diameter. Mention L means it will have unit of length.
Yes, sir.
Okay, this is the dimensions. So this Boltzmann constant will have unit of mass, length square, time square, temperature.
Sir, but in molar heat also it is there. So molar heat, how time will come? Like,
So it will come actually. Molar heat capacity at constant volume. This is L square T square, na?
sir, L is length and T is okay. T is dimensionless time.
Not dimensionless time. It is time.
Okay, sir.
So joule, how joule is related with meter?
Joule is force into displacement. So joule
And
joule upon Newton is equal
force is
to,
mass into acceleration.
yes,
In
sir.
acceleration, there is a time, na?
Oh, okay. I get it, sir.
Okay. So if you
Yes,
convert that equation of heat capacity in, this is length square, meter square, second square, and T is temperature.
right, sir.
Okay. Similarly, thermal conductivity is also there is a time.
Yes, sir. I get it now.
Okay. So that joule is related. Okay. You can correlate that PV equals to work, pressure into volume. Okay. Pressure is
P-
force per unit area.
Yes, sir.
PDV is work, and work generally represented in terms of joule. From there, that joule is related to temperature somehow. You can just have unit manipulation, then you will get that.
Yes, sir. Okay, sir. I've got it now.
Okay. So anybody else?